Have you ever, found yourself scrolling through the news and your eyes just kind of glaze over? You see a headline like, uh, new study reveals 73% of people prefer pesto to marinara.
Happens all the time.
Right. Or maybe a health claim, something like drinking green tea guarantees longevity. And you just sit there thinking, how on earth did they figure that out?
Yeah, where do those numbers come from?
Exactly. Can I even trust that number? We are absolutely swimming in data, statistics, bold claims every single day. And often we don't really have the tools, the fundamental understanding to decode what's being thrown at us.
It's overwhelming for sure.
Well, that's precisely what we do here on the Deep Dive. We take those complex, sometimes really overwhelming topics, and we sort of unspool them. We sift through all the information, pull out the most important bits, the key knowledge.
Nuggets, yeah.
And then we hand them over to you, our listeners, so you can be well-informed, quickly, and thoroughly. And today, we're embarking on a deep dive into something that might, well, at first blush, sound a little intimidating, maybe even a bit dry. AP statistics.
Ah, yes, good old AP stats.
But I promise you, this isn't just about high school textbooks or, passing some exam. This is really about equipping you with a genuine superpower.
Ooh, I like the sound of that. A superpower.
Yeah. The ability to actually understand the language of data that just surrounds us constantly. And maybe even more importantly, to spot the insights hiding right there in plain sight.
That's the perfect way to put it. Think of AP statistics not as this mountain of formulas you got to memorize, but really as an incredibly powerful toolkit.
Okay.
Yeah, a comprehensive language, actually, that allows you to truly speak with and understand the data that influences so much of our world. This deep dive, it's designed to demystify statistics.
Yeah.
I want to give you a clear roadmap. Our goal isn't just about teaching you how to crunch numbers, but how to think critically, how to ask the right questions, and ultimately how to make data your most trusted ally rather than something that feels like this impenetrable enemy.
An ally, not an enemy. I like that.
It's really about cultivating that wisdom, the wisdom to tell the difference between a truly significant finding and just, well, statistical noise.
And that really is our mission today. We're going to distill the absolute core concepts of AP statistics, highlight their frankly surprising real-world applications,
They really are everywhere.
and provide you, our listener, with the insights you need to gain knowledge quickly but thoroughly. You'll get a foundational framework, a new lens for understanding the world around you in a whole new, much sharper way. Okay, let's unpack this.
Let's do it.
So let's begin by painting a sort of broad, sweeping picture of what AP statistics actually covers. I like to think of it like embarking on a grand journey.
A journey, nice.
Or maybe like using a really comprehensive map. It guides us from these raw, often kind of messy observations all the way to confident, well-reasoned conclusions. The course itself is structured around 9 major units.
9 units.
But these 9 units, they all elegantly feed into what the College Board is. They're the ones who oversee the AP curriculum calls 4 big ideas.
The big 4.
Exactly. And believe me, these aren't just abstract categories. They represent a really logical, progressive pathway in how we learn to approach and interact with data.
Step by step.
The first of these big ideas, and arguably the starting point for any good data exploration, is exploring data.
Makes sense. Start there.
Right. It's literally just about looking at what we have, figuring out how to describe it, how to summarize it, how to visualize it effectively. It's that very first step in making sense of what might initially seem like just a giant pile of numbers.
Getting your bearings.
Then, once we get good at describing, we naturally ask, okay, where did this data even come from? And that leads us straight into the second big idea, sampling and experimentation.
Crucial. Absolutely crucial.
This is all about how we get good, trustworthy data in the first place. Because let's be honest, if your initial data is flawed, right, if it's collected poorly.
Garbage in, garbage out, as they say.
Exactly. Then everything else you do with it, all the fancy analysis, it really doesn't matter much, does it?
It's completely foundational. You nail it there. And once you've described your data and you feel confident about how it was collected, the journey continues.
We move to the third big idea. Anticipating patterns.
Okay, anticipating patterns.
This is where we dive into the really fascinating realms of probability and simulation. It's about understanding randomness itself, that mysterious dance of chance that underlies so much of our world.
From coin flips to drug trials, exactly.
Yeah.
It's about predicting the likelihood of certain events happening. And then finally, we arrive at the grand culmination.
Yeah.
The reason we do all of this in the first place, statistical inference.
The big payoff.
That's it. This is where we take everything we've learned, how to describe data, how to collect it well, how to understand the underlying probabilities, and we use it to make smart, evidence-based guesses, inferences, about a much larger world.
Based only on our limited observations, our samples.
Based only on our samples. That's the power of it.
That narrative flow you mentioned, it feels absolutely crucial because each unit really does build on the last one, doesn't it?
It really does. It's a very logical progression.
You start with the basics, like describing just one set of numbers. Then you move on to exploring these sometimes complex relationships between two sets of numbers. From there, you learn the art and really the science of collecting data reliably. Then you unlock the underlying rules of chance, the probability stuff, and at last, you get to use all of that built-up knowledge to draw these powerful, generalizable conclusions about whole populations.
It's less about rote memorization, like you said earlier, and much more about learning a robust, repeatable process of discovery.
A process.
It really is like learning to read a secret language. And once you decipher it, it reveals these hidden truths about populations, about trends, even about those really elusive cause and effect relationships that you just wouldn't be able to see otherwise.
It's kind of a joy when you see it click for people, isn't it?
Oh, absolutely. That aha moment is fantastic.
All right, so let's start right at the beginning, like peeling back the first delicate layer of an onion. We're going to dive into what's typically covered in Units 1 and 2 of AP Stats. It's all about describing our world. And the fundamental question here is, how do we even begin to make sense of what looks like a chaotic pile of numbers?
Well, it all starts with classification, really. You got to know what you're dealing with. Unit 1 is specifically called Exploring One Variable Data, and its core idea is understanding what we call distributions of a single variable.
One variable at a time.
Exactly. And the very first, most fundamental distinction we must make when looking at any data set is whether a variable is categorical or quantitative.
Okay, categorical versus quantitative. Why is that so important?
Because it profoundly dictates everything about how you can analyze that data later. It sounds minor, but it's huge.
That's right. It's like the fork in the road. So let's break it down. Categorical variables. Those are the ones that place individuals into distinct groups or categories, right?
Yep. Think groups.
Like asking someone their favorite color, red, blue, green, yellow. Or maybe their political party, Democrat, Republican, Independent. Or even a simple yes-no, like did you vote? These are categories. You can count how many people fall into each group, sure. But you absolutely cannot, for example, find the average political party.
Doesn't make sense.
Or say that blue is numerically more than red. It's just meaningless.
Precisely. And then, in contrast, you have quantitative variables. These are the ones that take numerical values that actually measure or count something.
Okay, like numbers that mean numbers.
Exactly. Think about someone's height in centimeters, their test score out of 100, the number of hours you spent doom scrolling today.
Uh-oh.
Or the temperature outside. These are all numerical values that you can and should perform mathematical operations on. You can find the average height, or the range of test scores, or how much the temperature varies.
This distinction, it seems simple, but it's so important. I mean, think about it. Why do we ask, what's your gender, as a categorical question, versus how old are you, as quantitative?
Right.
Because trying to find the average gender would be completely nonsensical. But finding the average age of a population, that tells you something incredibly useful, really insightful.
Yep.
So, for you, our listener, this basic understanding helps you immediately identify what kind of data you're looking at, which then, crucially, dictates the right analytical tools you should even think about using. It's like your first step to being a data detective.
Your first clue.
Okay, so once we've classified our data categorical or quantitative, how do we then effectively describe its distribution? Especially for quantitative data, we use a super helpful and pretty memorable acronym, SOCS.
SOCS. Gotta love the acronyms.
Don't we all? It stands for shape, outliers, center, and spread. This is our essential sort of foundational framework for describing any pile of numbers. Gives us the whole picture.
Let's focus on center first. Two very common measures here, and they often get confused. The mean and the median.
Ah, yes. Mean versus median.
The mean is what most people just instinctively think of as the average. You add up all the numbers, divide by how many there are. Simple, right?
Seems simple enough.
But here's where it gets really interesting. And where, honestly, a lot of people have that first real aha moment in statistics. The mean is incredibly sensitive to extreme values.
Those outliers we mentioned in SOCS.
Exactly. Those outliers. The mean gets pulled around by them quite easily.
You bet it is. It's like the mean is easily swayed by, I don't know, the loudest voice in the room,
Yeah,
right?
that's a great analogy.
The median, though, is completely different. It's just the middle value when you line all your data points up from smallest to largest.
50% below, 50% above.
Right. Half the observations are below it, half are above.
Mm-hmm.
And what's truly fascinating here, what makes the median so powerful, is that it is incredibly resistant to those outliers.
It stands its ground.
It's the quiet, consistent one. Doesn't get flustered by extremes.
To really feel this, let's imagine a small tech startup. 5 employees, okay? 4 of them are earning a very respectable $60,000 a year.
Okay, solid.
But then there's the founder, and the founder's taking home a cool $1 million a year.
Wow, okay. Big difference.
Now, if you calculate the mean salary for this company, you add the 4 $60K salaries and the $1 million, divide by 5, it jumps all the way up to $232,000.
Sounds amazing for the company average.
Sounds fantastic.
No, right?
But does that number actually tell you about the typical salary for an employee there?
No, not really. It feels misleading.
Not really at all. Now look at the median salary. Line them up. 60K, 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 1 million. The one in the middle.
Still $60,000.
Still $60,000. Now, which number actually tells you about the typical salary for an employee at that company?
The median, clearly.
The median, without a doubt. And this distinction helps you understand why, for instance, things like housing prices or incomes are almost always reported using the median, not the mean.
Ah, that makes sense.
Because it gives a much more representative, more grounded picture, especially when the data is skewed, pulled by a few extreme values. It's a critical insight for navigating real-world financial news.
Absolutely. The mean can be easily fooled, like you said, by a few outliers, while the median is the resilient, grounded one. It's a fantastic example of how these concepts immediately help you see the real story the data's trying to tell. Okay, next up, still under the S for spread. In SOCS, we have the undisputed king of spread for quantitative data, the standard deviation, or SD.
SD, yeah. Gets thrown around a lot.
It does. What is it exactly? The standard deviation is, roughly speaking, the average distance that individual data points tend to be from the mean.
Okay, typical distance from the average.
Yeah. So a larger standard deviation means your data points are more spread out, more variable, while a smaller standard deviation means they're clustered really tightly around the mean. It indicates more consistency.
To illustrate this, let's maybe go back to our light bulb example. Remember that.
Sure, light bulbs.
Imagine you're comparing 2 different brands of LED light bulbs. Both brands might boast the same average lifespan. Let's say it's 25,000 hours. That's their mean lifespan.
Okay, same average.
But what if brand A has a much smaller standard deviation in its lifespan than brand B? What does that actually mean for you, the consumer?
Smaller SD means less spread out, more consistent.
Exactly. It means brand A's bulbs are incredibly consistent. They reliably last very close to that 25,000 hours. Brand B's bulbs, though, with their larger standard deviation. Well, some might burn out after only 10,000 hours, while others might last an incredible 40,000 hours.
So the average is the same, but the experience is totally different.
Totally different. Brand A offers far more predictability, more reliability. Understanding standard deviation helps you gauge that consistency, predictability, even risk in everything from product performance to, say, investment volatility.
That's a really valuable insight. It's not just about the average.
It's definitely not just about the average. Spread matters.
And then, almost magically, it seems, we encounter the normal distribution, universally recognized as the famous bell curve.
The bell curve, everyone's seen it.
It's beautifully symmetric. It has that one distinct peak right in the middle, and it just shows up with surprising regularity in both the natural world and in human phenomena.
It's kind of amazing how often it appears.
Think about things like the distribution of people's heights in a large population, or maybe SAT scores, or even those tiny measurement errors in really precise scientific experiments. They often follow this beautiful, predictable pattern. There's a certain, joy in discovering how common this shape actually is.
And the joy becomes even greater when you realize how simple it can be to interpret once you get the hang of its core property. For any normal distribution, we have the empirical rule.
The 68, 95, and 99.7 rule.
That's the one. often called the 68, 95, 99.7% rule, and tells us that for any normal distribution, approximately 68% of the data falls within one standard deviation of the mean.
Okay, the bulk of it.
About 95% falls within 2 standard deviations.
Most of it.
And virtually all of it, 99.7%, falls within 3 standard deviations of the mean.
Wow.
So if you know a population's height distribution is normal, and you know its mean and standard deviation, you can instantly estimate what percentage of people fall into a certain height range without doing complex calculations. It's an incredibly powerful shortcut.
And that remarkable rule, it leads us directly to z-scores, doesn't it?
It does indeed. Think of a z-score as a kind of universal ruler.
A universal ruler. How so?
A z-score tells you precisely how many standard deviations away a particular data point is from the mean of its distribution.
Okay, so it standardizes things.
Exactly. For example, if you scored a plus 2.0 z-score on a biology test, it means your score was 2 full standard deviations above the class average for that test.
Which sounds pretty good.
It's very good. And what's incredible is that this allows you to compare seemingly incomparable things, like, say, your performance on a standardized math test versus a standardized verbal test, even if they had completely different scoring scales, different means, different standard deviations.
Because the z-score puts them on the same scale.
Precisely. A z-score puts everyone and everything on the same playing field for comparison. It tells you the relative position.
Yeah.
It's truly a game changer for comparison and understanding where a value sits within its distribution.
Okay, that wraps up the basics of one variable. Now let's zoom out a bit for Unit 2, exploring 2 variable data. This is where things get even more fascinating, I think, because we move beyond just describing one set of numbers. And we start asking, how do 2 variables relate to each other? Is there some kind of connection here?
Exactly. We're looking for those hidden connections, those relationships that might explain things. And the first, most visually intuitive tool in our statistical arsenal here is the scatter plot.
Scatter plots, little dots on a graph.
Little dots, but they tell a big story. It's a simple yet incredibly powerful graphical display specifically designed for showing the relationship between 2 quantitative variables. Each point on the graph represents one individual,
Okay.
with their x-coordinate being their value on one variable and their y-coordinate being their value on the other variable.
And just by looking at it, you can see a pattern.
You can. By looking at the scatter plot, we can immediately begin to see the story unfold. Is there a general pattern, what we call the form? Is it roughly straight or is it curved?
Right.
What's the direction of the relationship? Is it positive, the meaning as one variable goes up, the other tends to go up too? Or is it negative, as one goes up, the other tends to go down?
Like temperature and ice cream sales would be positive.
Perfect example. And finally, what's the strength of that relationship? How tightly do the points cluster around that recognizable pattern? Are they really close together or scattered all over the place?
And to actually put a number on that linear relationship, to quantify it precisely, we use the correlation coefficient, right? Little r?
That's the one. Little r.
Yeah.
This number is surprisingly powerful, and it always falls somewhere between -1 and +1.
Okay, -1 to +1.
An r value close to +1 signifies a strong, positive, linear relationship, like your ice cream sales versus temperature example. You'd expect to see a very strong, positive, linear relationship, and you'd likely find a high positive r value, maybe 0.85 or even 0.90.
Makes sense.
Conversely, if r is near modic 1, it indicates a strong, negative linear relationship. As one variable increases, the other tends to decrease linearly.
Like maybe hours spent studying and number of mistakes on a test.
Potentially, yeah, although maybe not perfectly linear. And if r is near 0, it tells you there's virtually no linear relationship at all. The points might still have a pattern, maybe a curve, but not a straight line one. Or they could just be randomly scattered.
So R measures linear association specifically.
Crucially, yes. Linear association is a remarkably concise summary of that specific type of relationship. And building on that idea of a linear relationship, we often move into linear regression. Specifically, finding the least squares regression line.
The line of best fit.
Exactly. It's essentially the mathematical line of best fit that we draw through that cloud of points on our scatter plot. It's called least squares because it's the unique line that minimizes the sum of the squared vertical distances from all the actual data points to the line itself. Basically, it gets as close as possible to all the points overall.
And the equation looks like basic algebra, right? Y hat equals a plus bx.
Familiar territory, tot plus bs. Here, we say y hat is our predicted value for the response variable based on a given value of the explanatory variable x.
And here's where the interpretation becomes absolutely critical, putting this into real-world context. The slope and the intersect.
Yes, B and A.
The slope B seems particularly insightful. It tells you what, for every 1 unit increase in our explanatory variable x, our response variable y is expected to increase or decrease by B units on average. Is that right?
Perfect interpretation. So if you're predicting house prices based on square footage, the slope, B, would tell you the average increase in price for each additional square foot of space. That's incredibly useful information.
Totally. And the intercept A.
The intercept A is the predicted value of y when x is exactly 0. Now, mathematically, it's necessary for the line, but sometimes predicting when x is 0 doesn't make any meaningful real-world sense.
Like your house price example, predicting the price of a house with 0 square footage.
Exactly. Doesn't mean anything practical. So you always have to consider if the intercept has a logical interpretation in the context of the problem. And a word of crucial caution here. We always need to check how well our regression line actually fits the data. We don't just calculate it and assume it's good.
How do we do that?
We look at the residuals and, importantly, we plot them. A residual is simply the difference between the actual observed value of y for a data point and the value that was predicted by a regression line for that same point.
So it's the error, the leftover bit.
Exactly. It's the leftover error, the part the model couldn't explain. When you plot these residuals against the explanatory variable, x,
Yeah.
you want to see, well, nothing. Just a completely random scatter of points like static on an old TV screen.
No pattern at all.
No pattern at all. If you see any kind of pattern, maybe the residuals form a curve or maybe they fan out, getting bigger as x gets bigger, that's a big red flag. It tells you that a linear model might not actually be the best fit for your data, or that there are other issues you need to investigate.
Okay, check the residual plot. Good tip.
And speaking of caution, we must be incredibly wary of extrapolation.
Predicting outside the known data range.
Precisely. That's like trying to predict, I don't know, what your life will be like when you're 90 based only on your habits as a teenager. It's a massive, often totally unreliable leap into the unknown. Stick to predictions within or very close to the range of your actual data.
Now, if there's one single statistical mantra, maybe one core truth that can give you a true aha moment and really profoundly change how you consume news and make decisions, it's this. Association is not causation.
Say it again. Louder for the people in the back.
Association is not causation. This is probably the most important lesson you can take away from this whole deep dive. Just because two variables are correlated or strongly associated does not automatically mean that one causes the other.
It's so tempting to make that leap, though.
It is, but association just means they're related somehow. Causation means one directly produces or brings about the other. Big difference.
This point is absolutely critical for, well, just critical thinking in general.
Yeah.
The classic example people always cite is the high correlation that's sometimes found between the number of TVs in a home and the average life expectancy in that region.
Right, more TVs, longer life. Doesn't make sense.
Does having more TVs magically make you live longer? Of course not. That's an absurd conclusion. What's almost certainly at play here is what we call a lurking variable.
Something hidden in the background.
Exactly. Something unmeasured that influences both variables. For instance, wealthier homes tend to have more TVs, and wealthier individuals often have better access to healthcare, better nutrition, safer environments, all of which contribute to longer lives.
So wealth is lurking there, influencing both TV ownership and lifespan.
Very likely. The TVs aren't causing anything directly. Wealth, or something related to it, is the more likely common underlying factor. This concept alone, truly internalizing correlation is not causation, will help you see beyond those surface-level connections you read about constantly.
In news reports, ads, even just personal observations.
Everywhere. It empowers you to ask deeper, more insightful questions. It's basically your shield against misleading claims.
Knowing how to describe data beautifully is fantastic. We've covered that. But what if the data itself is flawed right from the start? What if it's biased or just doesn't represent who you think it does?
Then all that brilliant analysis is built on sand.
Exactly. It becomes meaningless. That's precisely where Unit 3, which we can call the art of collection, comes in. This unit is all about mastering the craft of getting data we can actually trust.
You're hitting on a crucial point. It really is like building a house. If that foundation is cracked, the whole structure is compromised no matter how fancy the paint job is.
Good analogy.
So let's get our foundational terminology straight first. We need to understand population versus sample, and alongside that, parameter versus statistic.
Okay, population versus sample, parameter versus statistic.
The population is the entire group of individuals you're truly interested in studying, all of them. For example, all registered voters in your state or every single tree in a national forest.
The whole kit and caboodle.
The whole thing. A sample, then, is the smaller, hopefully representative, measurable subset of that population that you actually collect data from.
The group you actually talk to or measure.
Right. So if you want to know the true average height of all adult humans in your country, that average height is your population parameter, often denoted by the Greek letter nuthrels or mean.
The true value we wish we knew.
The true value. But you can't measure everyone. So you meticulously measure a sample of, say, 1,000 adults. The average height of that sample, that's your sample statistic, often denoted by the X bar for the sample mean.
So the parameter describes the population, the statistic describes the sample.
You got it. The parameter is the truth. The statistic is our estimate of the truth based on our sample.
And the whole goal, then, is for that sample statistic to be a good, reliable estimate of the population parameter.
That's the name of the game.
And to achieve that, you absolutely need good sampling methods. What's the best approach?
The undisputed gold standard, the ideal we always strive for, is the simple random sample, SRS.
SRS. Okay. What makes it simple and random?
In a true SRS, every possible group of individuals of the desired size has an exactly equal chance of being selected. It's truly like putting everyone's name into a giant, well-mixed hat and drawing out your sample completely randomly. This ensures fairness and, crucially, helps ensure the sample is representative.
So no favoritism in who gets picked.
None whatsoever. Now, while SRS is the ideal, it's not always practical. So we have other clever methods, too. For instance, stratified random sampling.
Stratified, like layers.
Exactly. You first divide your population into homogeneous groups, or strata, based on some characteristic, is important. It might affect the results, maybe age groups or income levels or geographic regions.
Okay, group them first.
Then you take a separate, simple random sample from within each of those strata. This is incredibly useful for something like an opinion poll, where you want to absolutely ensure that different demographics, like different age groups, are properly represented in your final sample in the same proportions they exist in the population.
That makes sense. Ensures balance.
It does. Then there's also cluster sampling. Here, you divide the population into larger, often naturally occurring clusters, like specific city blocks, or maybe all the students in randomly chosen classrooms within a large high school.
Okay, bigger groups.
You then randomly select a few of these entire clusters, and you survey everyone within those chosen clusters. This could be much more practical and cost-effective than trying to get an SRS from a huge, spread-out population.
Got it. So different random ways to pick people.
The key overarching idea, though, regardless of the specific method, SRS, stratified, cluster, is that random sampling is absolutely crucial if you want to legitimately generalize your results from your sample back to the larger population it came from.
Randomness is key for generalizing.
Without randomness, you're building on shaky ground. Your conclusions might only apply to the specific, potentially weird group you happen to sample.
And just as important as using good sampling methods is being able to recognize when things go wrong, recognizing the presence of bias in sampling.
Bias is the enemy of good data.
What is bias, fundamentally?
Bias, at its core, is a systematic favoritism in your sampling method that consistently leans towards certain outcomes or certain types of individuals, leading to results that aren't truly representative of the population. Think of these biases as, like, data saboteurs trying to trick you.
Data saboteurs, I like that. What are some common ones?
Well, one common saboteur is selection bias, which is often called undercoverage. This happens when some groups in the population are systematically left out of the process of choosing the sample, or they just have a much lower chance of being included than others.
Like they're just missed entirely.
Yeah. Imagine a historical phone survey that only calls landlines. It would completely miss everyone who only uses a cell phone, right?
Yeah.
Which today is a huge chunk of the population, so it systematically undercovers that group.
Okay, undercoverage. What else?
Then there's non-response bias. This occurs when individuals are selected for the sample, but then they refuse to participate. Or maybe you just can't contact them.
So they were chosen but didn't answer. Why is that a bias?
The problem is that the people who don't respond often differ in significant ways from those who do respond. Think about a product satisfaction survey. If only the really, really angry customers bother to fill it out.
You're going to get a very negative picture.
Exactly. You get a wildly biased and overly negative picture of overall satisfaction because the reasonably happy people didn't bother responding. Their voices are missing.
And don't forget response bias. This is a tricky one. This is when the answers themselves are inaccurate, even if people do respond.
How does that happen?
It can creep in due to surprisingly subtle factors. Like the wording of a question if I ask, do you agree with our wonderful new policy that will save puppies from harm?
You're kind of leading the witness there.
Totally. You're
Huh.
probably more likely to say yes, right? Or maybe the interviewer's demeanor influences responses. Or even just social desirability, where people give answers they think are more socially acceptable or that make them look better rather than their completely honest truth.
Ah, yeah. People might not admit to certain behaviors.
Right. And finally, maybe the most common and often most egregious data saboteur is voluntary response bias.
Voluntary response.
Yeah.
Like people choose to join in.
Exactly. This happens when people self-select to participate in a survey or poll. Think of those online polls you see on news websites, or call-in radio shows where they ask for opinions.
Oh, yeah, those are everywhere.
Typically, only people with very strong opinions, often on the extreme ends of the spectrum, bother to respond. People who feel meh usually don't participate. So the results are heavily skewed by the passionate few and don't reflect the broader population at all.
It's just the loudest voices again?
Pretty much. Becoming a true data detective really starts with your ability to spot these biases, under coverage, non-response, response, voluntary response, and realize when the data you're looking at might be trying to pull a fast one on you.
It's about asking, how was this data actually collected?
Critical question.
Now, following on from sampling, we come to a really crucial distinction for understanding claims, especially those you see in the media, the difference between experiments and observational studies.
Okay, experiment versus observation. What's the key difference?
In an observational study, as the name kind of suggests, we simply observe and collect data on individuals without trying to charge anything. We don't impose any treatments,
Just watching.
just watching. For instance, maybe tracking a group of people who choose to smoke and a group who choose not to smoke for 20 years, and then comparing their rates of lung disease. We're just watching and recording what naturally occurs.
Okay, makes sense. So what's an experiment then?
In an experiment, it's fundamentally different. Here, we, the researchers, actively impose a treatment on individuals specifically to see if it causes a change in their response.
Ah, we do something to them.
We intervene.
Yeah.
We might give one group of patients a new drug and another group a placebo, a fake drug, and then compare their health outcomes. This distinction leads to probably the single most crucial insight in this entire section.
Okay, lay it on me.
Only well-designed experiments can establish causation.
Only experiments can prove cause and effect.
That's it. Observational studies, because you're merely watching and not controlling all the other factors that might be involved, can only show an association or a correlation. They simply cannot prove cause and effect.
Why not? What's missing in the observational study?
Control. You can't legitimately conclude, for example, that going to college causes higher income based solely on observing that college grads tend to earn more. Why? Because there are simply too many other potential factors, those lurking variables we talked about.
Right, lurking variables again.
Things like pre-existing intelligence, family wealth and connections, personal ambition, the specific major they chose. All of these might be associated with both attending college and earning more money later. The college itself might not be the direct cause, or at least not the only cause.
Okay, too many confounding factors you can't separate out.
Exactly. But conversely, a well-controlled experiment could potentially test if, say, a specific new teaching method causes higher test scores. How? By randomly assigning students to either the new method or a traditional method, keeping everything else as similar as possible. That deliberate intervention and randomization is the key to potentially showing causation.
And for those experiments to be considered truly well-designed, they need to follow certain powerful design principles, right? You called them superheroes earlier.
The superheroes of good data collection, yes. First, there's control. This means actively minimizing the influence of other variables, those lurking variables that could potentially mess up your results. Often this involves using a control group.
The group that doesn't get the main treatment.
Right. They might get no treatment or a standard existing treatment, or maybe a placebo, a fake treatment that looks just like the real one. This helps you account for the placebo effect, where people feel better just because they think they got a treatment.
Okay, control group and placebo. What else?
Then absolutely essential, especially for establishing causation, is random assignment.
Randomly putting people into the treatment groups.
Yes. By randomly assigning subjects to different treatment groups, like the drug group versus a placebo group, You create groups that are, on average, incredibly similar in every way imaginable except for the treatment they receive.
So any differences you see later are likely due to the treatment.
That's the goal. It helps isolate the effect of your treatment, making sure that observed differences are truly due to the treatment itself and not some pre-existing difference between the groups that you didn't account for.
Makes sense. What are the other superheroes?
Replication. This simply means using enough subjects within each treatment group. You can't run an experiment with just like 2 people in each group. You need a sufficient number of observations to see the real effects of the treatment and to ensure that what you're seeing isn't just due to random chance or a couple of really unusual individuals.
Need enough data points.
Exactly. Blinding is also incredibly important. This means that the subjects, and sometimes even the researchers interacting with them, are unaware of which treatment group a subject is in.
Why keep them in the dark?
To avoid bias. If subjects know they're getting the real drug, they might report feeling better just because of that expectation, the placebo effect again. If researchers know who got which treatment, they might subtly, even unconsciously, evaluate the outcomes differently. A double-blind experiment, where neither subjects nor researchers know, is often the gold standard.
Okay, blinding. And one more.
Blocking. This is a smart strategy you can use before you randomize. If you know there's some characteristic of your subjects that might strongly influence their response, like maybe age or severity of illness, you can group similar subjects together into blocks first.
Like the stratified sampling idea, but for experiments.
Very similar concept. For example, in a drug trial, you could block by age group, 20, 30, 31, 40, etc., and then randomly assign treatments within each age block. This helps reduce unwanted variability caused by that blocking factor and makes your experiment more sensitive to detecting the actual treatment effect.
Clever. So, control, random assignment, replication, blinding, blocking, the experiment, superheroes.
They protect your data integrity.
All of this careful collection, whether it's sampling or experiments, it leads us to a really crucial concept called scope of inference.
Scope of inference sounds important.
It is. This is basically your personal guide to understanding what conclusions are actually valid from any study you encounter. It tells you exactly what you can legitimately claim based on how the data was collected.
Okay, what are the rules?
Rule number 1. If a study used random selection to choose its sample from a larger population.
Like an SRS or stratified sample.
Right. Then, and only then, can you confidently generalize your findings from the sample to that larger population from which the sample was drawn.
Random selection allows generalization to population.
Got it. Rule number 2. If the study used random assignment of subjects to treatments in a well-designed experiment.
Like in our drug trial example.
Exactly. Then, and only then, can you confidently infer causation. You can potentially claim that the treatment caused the observed difference in outcomes.
Random assignment allows inference of causation. Got it.
This is absolutely vital for you, the listener, when you're evaluating any news story about a new study or survey. The next time you read a headline, ask yourself, did they use random selection? If so, can they generalize these findings? Did they use random assignment in an experiment? If so, can they genuinely claim cause and effect? Or are they maybe overstating their conclusions based on just an observational study?
Knowing this framework really empowers you to critically assess information and not just blindly accept headlines.
It's your critical thinking toolkit right there. Okay, now that we've mastered the art of getting good, trustworthy data, let's dive into the fascinating, sometimes baffling force that seems to govern everything around us. Randomness. We're talking units 4 and 5 now, exploring the dance of chance and what to expect.
Probability, where things get really interesting and sometimes a little weird.
Unit 4 is dedicated to probability, random variables, and probability distributions. The core idea here is all about quantifying uncertainty, right? And understanding the long-run behavior of random events.
Exactly. Probability, at its simplest, is just a number between 0 and 1. 0 means impossible, 1 means certain. It represents the proportion of times an event would occur if you repeated the random process over and over and over again, a very, very long series of times.
So it's not about predicting a single coin flip.
Nope. Can't do that reliably. But it is about predicting what happens over, say, 1,000 coin flips. You'd expect about 500 heads.
And building on that basic definition, we learn the foundational rules of probability, things like the complement rule.
The probability of something not happening is 1 minus the probability that it does happen. Simple but useful.
Right. Or the addition rule for disjoint or mutually exclusive events, those that can't possibly happen at the same time.
Like rolling a 1 and a 6 on a single toss of one die? Can't happen. So you add their probabilities if you want the chance of rolling a 1 or a 6.
And the multiplication rule for independent events.
Independence. That's a truly key concept to grasp here. Two events, let's call them A and B, are independent if knowing that one event occurred doesn't change the probability of the other event occurring at all.
Like coin flips again?
Perfect example. The probability of getting heads on your next coin flip is completely independent of what you got on the previous flip. Coins don't have memory, thankfully.
Thankfully.
But contrast that with a different scenario. The probability of needing an umbrella, given that it's cloudy outside.
The cloudiness definitely changes the probability of needing an umbrella.
It sure does. That's a conditional probability. One event, the cloudiness, changes the likelihood of the other event, needing an umbrella. We denote it as PAB, the probability of A happening given that B has already happened. Understanding independence versus dependence is crucial.
We also dive into random variables and their expected value. What's a random variable?
It sounds fancy, but it's simply a variable whose value is a numerical outcome of a random process. Like if you flip a coin 10 times, the number of heads you get is a random variable. It could be 0, 1, 2, all the way up to 10.
Okay, a number determined by chance and expected value.
The expected value, which is essentially the mean of that random variable, is the long-run average outcome if you were to repeat that random process many, many times.
The average result over the long haul.
Exactly. And this concept has truly fascinating real-life applications. If you were to calculate the expected value of playing a typical lottery game, for instance.
Let me guess. It's not good for the player.
Almost always, it's a negative number, meaning that, on average, in the long run, you are actually expected to lose money every time you buy a ticket.
So the house always wins.
Pretty much. It's precisely how casinos and lotteries thrive. They set up games where the expected value for the player is negative, ensuring their own long-term profitability. It's a powerful lesson in making smart choices when chance is involved.
Definitely makes you think twice about buying that ticket.
It should. We also examine specific common probability scenarios, like the binomial distribution. This is used for counting the number of successes in a fixed number of independent trials, where each trial has the same probability of success.
Like your free throw example earlier, number of successes out of 10 attempts.
Exactly. Calculating the probability of making exactly 7 successful free throws out of 10 attempts, assuming each shot is independent and has the same chance of going in, that's a binomial setting. Then there's the geometric distribution.
Geometric, how's that different?
Geometric is also about independent trials with the same success probability, but instead of a fixed number of trials, it helps us determine the number of trials until the very first success occurs.
So how many attempts until you make your first free throw?
Precisely. How many times do you have to flip a coin until you get the first head? That's a geometric setting. These specific distributions provide powerful models for understanding very common types of random processes.
And underpinning all of this probability stuff is a really comforting, almost poetic truth known as the law of large numbers.
The law of large numbers. Sounds grand.
It is. It basically states that as you perform more and more trials of a random process, the observed proportion or frequency of an event happening will get closer and closer to its true theoretical probability.
So things average out in the long run.
Exactly. While you can't predict your next single coin flip, you can be very, very confident that after, say, 1,000,000 flips, the proportion of heads you observed will be incredibly close to the true probability of 0.5. It provides stability amidst randomness.
What's truly fascinating here, and what makes Unit 5 sampling distribution such a pivotal section, is how it acts as this crucial bridge.
A bridge between what?
Between the world of pure probability we just discussed and the really exciting realm of statistical inference we're about to explore. This unit is fundamentally about understanding how our sample statistics, things like a sample mean or a sample proportion, behave when we take many, many different samples from the same underlying population.
Okay, so not about individual data points, but about the statistics we calculate from samples.
Exactly. How do those statistics themselves vary from sample to sample?
So to really visualize this, imagine you're trying to estimate the average weight of, say, a particular type of apple grown on a huge farm. You can't weigh every single apple, right?
It's impractical.
So instead, you take one random sample of 50 apples and calculate their average weight. Let's say you get 150 grams.
Okay, one sample average.
Then you go back, take another random sample of 50 apples and calculate their average weight. Maybe this time you get 155 grams.
A bit different. Makes sense.
And you repeat this process hundreds, maybe even thousands of times,
Yeah.
each time getting a potentially slightly different sample mean. The sampling distribution isn't the distribution of the weights of individual apples.
No.
It's the distribution of all those hundreds or thousands of average apple weights you just calculated. It's the distribution of the sample means.
Ah, okay. A distribution of statistics.
And it beautifully illustrates how much your sample statistic, in this case, the mean weight, is likely to vary from sample to sample purely due to the random chance involved in which apples ended up in which sample.
And here is where the real magic, the profound power of statistics, truly happens, with the central limit theorem, or the CLT.
The CLT, I've heard this is a big deal.
It is genuinely one of the most powerful and honestly surprising theorems in all of statistics. The CLT states something remarkable. If your sample size is large enough.
How large is large enough?
Well, there are conditions, but generally, for sample means, a sample size of 30 or more, 30 R1, is often a good rule of thumb. The amazing part is, if your sample size is large enough, then the sampling distribution of your sample means, or proportions, will become approximately normal in shape.
Wait, even if the original population wasn't normal?
That's the magic. Regardless of the original shape of the population's distribution, even if you're measuring something really weirdly shaped, like maybe reaction times, which are often skewed,
Okay.
if you repeatedly take large enough samples, say N50, and calculate the average reaction time for each sample, the distribution of those averages will start to look like a beautiful, symmetric, normal bell curve.
That is the aha moment right there. It's incredible.
It really is.
Think about it. Individual cat weights in a shelter might be a bit skewed. Lots of average cats, a few tiny kittens, maybe a couple of really plump ones. The distribution of individual weights might not look normal at all.
Right, could be lumpy or skewed.
But if you repeatedly take random samples of, say, 30 cats and average their weights, the distribution of those averages will start to look like that nice, predictable bell curve.
And this is precisely why things like political polls can work so effectively, even when we have no idea what the true distribution of opinions in the entire population actually looks like.
Because the distribution of the sample proportion will be approximately normal if the sample is big enough.
Exactly. This theorem is an absolute cornerstone of statistics because it allows us to use all the nice predictable properties of the normal distribution, like the empirical rule or using z-scores, to make incredibly powerful inferences about populations, even when we have no clue what the original population's shape looked like. It's truly liberating for statistical analysis.
Wow. The CLT, definitely a key takeaway.
And closely related to the central limit theorem is the concept of standard error.
Standard error, how's that different from standard deviation?
Good question. They sound similar. Remember, standard deviation, SD, tells you how much individual data points typically vary from the mean within a single sample or population. Standard error, SE, on the other hand, is specifically the standard deviation of a sampling distribution.
Ah, the standard deviation of all those sample means or proportions we were just talking about.
Precisely. While standard deviation measures variability of individuals, standard error measures the variability of a sample statistic, like $GIST, from sample to sample. It tells you the typical amount a sample statistic is likely to vary from the true population parameter just due to random sampling luck.
So a smaller standard error is better, means our estimate is more reliable.
Exactly. A smaller standard error means our sample estimate is generally more precise, less variable from sample to sample, and likely closer to the true population parameter. It gives us greater confidence in our conclusions. And guess what influences standard error? Sample size. Bigger samples lead to smaller standard errors.
Ah, that makes intuitive sense. More data, more precision.
You got it.
Okay, this is where statistics truly transcends just describing things and becomes incredibly powerful. We take everything we've learned describing data, getting good samples, understanding probability and sampling distributions, and we use it all to make educated guesses and confident statements about entire populations based only on our limited samples. This is the heart of statistical inference, which covers the last big chunk, Unit 6, 7, 8, and 9.
This is where we really start making claims about the world.
When we're doing inference, we typically start with a point estimate. What's that?
A point estimate is simply our single best guess for the value of an unknown population parameter. For example, we use our sample mean as our point estimate for the true unknown population mean, or we use our sample proportion as our point estimate for the true population proportion.
Just our best guess from the sample.
Your single best number. But we know, right, that a single estimate isn't enough. Because we're working with a sample, there's always inherent uncertainty. Our sample might not be perfectly representative just due to random chance.
Right. The next sample would likely give a slightly different estimate.
Exactly. So we need to acknowledge that uncertainty. We do this by adding a margin of error, MOE. Think of the margin of error as a crucial buffer of uncertainty that we place around our point estimate.
Like a plus or minus value.
Precisely. Like in political polls when they say plus or minus 3%, it acknowledges that our single sample estimate probably isn't exactly right, but the true value is likely within that range.
And this leads directly into the core idea of confidence intervals, which are covered extensively in Units 6 and 7.
Right. Instead of just giving that single point estimate, the whole idea of a confidence interval is to provide a plausible range of values for the population parameter we're trying to estimate.
A range instead of a single number. How is it structured?
The general structure usually looks something like this. You take your point estimate and you add and subtract the margin of error. And that margin of error is typically calculated as a critical value, which depends on your chosen confidence level, multiplied by the standard error of the statistic.
Okay, so estimate critical value X, standard error.
That's the basic recipe for most common confidence intervals.
So let's go back to that political poll example. If a reputable poll report, say, a 95% confidence interval for the proportion of voters supporting candidate X is 48% to 52%, or 0.48 to 0.52, what does that interpretation really mean?
The standard interpretation is, we are 95% confident that the true population proportion of all voters who support candidate X is actually somewhere between 48% and 52%.
We're 95% confident the truth is in that interval.
That's the common phrasing. And you see confidence intervals used everywhere, right? Not just political polls. Maybe estimating the average defect rate for products coming off an assembly line, or assessing the average effect of a new fertilizer on crop yield in agriculture.
Yeah, they seem really practical.
Now, here's a crucial nuance. A subtlety that many people, even folks who've taken stats, often misunderstand about that confidence level, like the 95%.
Okay, what's the common mistake?
It's not technically correct to say that there's a 95% probability that our specific interval, say that 48% to 52%, contains the true parameter.
Wait, really? That sounds like what it means.
It sounds like it, but it's slightly different. The true parameter is a fixed, unknown number. It's either in our calculated interval or it's not. The probability is either 1 or 0 for that specific interval. The confidence level actually refers to the long-run success rate of the method we use to construct the interval.
The method, okay, explain that.
It means that if we were to repeat the entire sampling process, take a brand new sample, construct a brand new interval using the same method many, many times, then approximately 95% of all the intervals we construct using this procedure would actually capture or contain the true unknown population parameter.
Ah, so it's about the reliability of the process, not the certainty of one specific result.
Exactly. It speaks to the reliability of the procedure itself over many repetitions. Understanding that distinction is key to truly accurately interpreting what a confidence interval represents. It's confidence in the method, not probability for the interval.
Got it. Confidence in the method. That's a key clarification. Now, beyond just estimating parameters with confidence intervals, we also perform hypothesis tests, right? Often called significance tests.
Yes. If confidence intervals are about estimating what is the value, hypothesis tests are about assessing evidence for a specific claim, like is the value different from X?
You called it a statistical courtroom earlier. I like that.
It's a good analogy. We have a specific claim about a population parameter, and we gather evidence from our sample data to see if that claim can withstand scrutiny. Does the evidence support rejecting the initial assumption?
And just like in a courtroom, we start by stating two competing claims, right? The null hypothesis and the alternative hypothesis.
Correct. The null hypothesis, $H a deal, is the status quo, or no effect or no difference claim. It's the default assumption we start with, much like assuming a defendant is innocent until proven guilty.
So, example.
Like $H. The new drug has no effect on average blood pressure, meaning the average change is 0. Or $H. The average weight of this product is exactly the claimed 10 ounces.
Okay, the nothing interesting is happening hypothesis.
Pretty much. The alternative hypothesis, then, is what we are actually trying to find evidence for. It usually represents what the researcher suspects or hopes is true.
Like
Hulk. The new drug reduces average blood pressure, meaning the average change is less than 0. Or average weight of the product is less than 10 ounces. if we suspect the company shortchanging customers. We're looking for evidence against the null hypothesis in favor of the alternative.
Innocent until proven guilty. Got it. And then we get to the core piece of evidence, that magic number that helps us decide the p-value.
Ah, the p-value. Probably the most famous and often most misunderstood concept in statistics.
It's our statistical evidence meter, you said. Explain how it measures evidence.
Okay, the p-value is a probability of observing a sample result, like a sample mean or proportion, that is as extreme or even more extreme than what we actually saw in our data, assuming that the null hypothesis, the H-dollars or rolls, were actually true.
Whoa, okay, say that again slowly. Probability of seeing our data or something even more unusual?
If the null hypothesis is the real truth, let's go back to our courtroom analogy. Imagine H-dollars a roll is the defendant is innocent. The p-value then tells you, okay, if this defendant were truly innocent, how likely would it be to see all this incriminating evidence we just gathered, or sample data, purely by random chance or coincidence?
Ah, so if that probability, the p-value, is really small.
Exactly. If the p-value is super small, say 0.03 or 3%, it means that seeing this much evidence against our innocent claim, if they truly were innocent, would be a very rare, very unlikely event. It only happens 3% of the time by chance if they're innocent.
Which makes us suspicious.
It makes us very suspicious. It suggests that our initial assumption, innocence or D-shell or dread, might be wrong. A small p-value provides strong statistical evidence against the null hypothesis, and therefore in support of the alternative hypothesis. A small p-value is your signal that something interesting might be going on.
Okay, small p-value is strong evidence against H-dollars. How small is small enough?
That's where the significance level comes in. This is our predetermined threshold of doubt. Before we even look at the data, we decide on an alpha level. It's very commonly set at 0.05 or 5%.
The famous 5% level.
That's the one. We then compare our calculated p-value to this alpha level. If our p-value is less than or equal to alpha, we make the decision to reject H-dollars. We conclude that we have statistically significant evidence against the null hypothesis. If the p-value is greater than alpha, we fail to reject H-dollars.
Fail to reject sounds a bit weak.
It's phrased carefully for a reason. Failing to reject H-dollars doesn't mean we've proven H-dollars is true. It just means we didn't find enough evidence in our current sample to reject it. Maybe the effect is real but small, or maybe our sample size was too small to detect it. We never accept the null hypothesis. We only fail to find sufficient evidence against it. Absence of evidence is not evidence of absence.
Okay, reject H-dollars or fail to reject H-dollars. Never accept H-dollars. Got it. But you mentioned errors earlier. Since we're making decisions based on probability, we can sometimes be wrong, right?
Absolutely. In statistics, we can never be 100% certain when dealing with samples. So there's always the possibility of making one of two types of errors in hypothesis testing. A type of error is like a false positive.
False positive.
This happens when we reject the null hypothesis, H-dollars, when in fact H-dollars was actually true. For example, concluding that a new drug works, rejecting H-dollar drug has no effect, when it truly has no effect at all.
Claiming something works when it doesn't. What's the chance of that?
The probability of making a type I error is exactly equal to our chosen significance level, alpha. So if we use alpha 0.055, we are accepting a 5% risk of making a type I error in the long run.
Okay, so alpha sets the risk of a false positive. What's the other error?
The other is a type 2 error, which is like a false negative.
False negative.
This occurs when we fail to reject the null hypothesis, H-dollars on it, when the alternative hypothesis is actually true.
No.
In simple terms, it's failing to detect a real effect or real difference when one actually exists.
Like failing to realize that a drug does work.
Exactly. Failing to detect that the drug is effective, failing to reject H-dollars drug has no effect when it truly is effective is true. The probability of type 2 error is denoted by the Greek letter beta.
Okay, type I, false positive, risk equals alpha. Type 2, false negative, risk equals to beta. Understanding the consequences of each seems critical.
Absolutely crucial in real-life applications. Think about a medical diagnostic test for a serious disease. Is it worse to have a type I error, a false positive, telling a healthy person they have the disease, causing anxiety and further unnecessary tests? Or a type 2 error, a false negative, telling a sick person they are healthy, delaying potentially life-saving treatment?
Wow, yeah. The answer really depends on the specific disease and the implications of each error.
Entirely depends on the context and the stakes involved. Statisticians and policymakers have to weigh these risks carefully.
And before we can trust any of these inference results, whether it's a confidence interval giving us a range or a hypothesis test making a decision, we absolutely must check the conditions for inference, right?
Non-negotiable. These are the prerequisites, the foundational checks that ensure our chosen statistical method is actually appropriate for the situation and that our results are trustworthy. If the conditions aren't met, our calculations might be mathematically correct, but the conclusions could be completely meaningless or misleading.
What are the typical conditions we need to check?
They vary slightly depending on the specific procedure, proportions versus means, one sample versus two, but generally they boil down to a few key ideas. First, the data must come from a random sample or a randomized experiment. We need randomness to make inferences.
Randomness again, always key.
Always. Second, individual observations usually need to be independent. When sampling without replacement, we check the 10% condition. Our sample size should be no more than 10% of the population size to ensure observations are effectively independent.
Okay, random, independent, or 10% condition. What else?
Third, the sampling distribution of our statistic needs to be approximately normal. This is where the central limit theorem often comes in. We need to check if our sample size is large enough. For proportions, we usually check if the number of expected successes and failures are both at least 10. For means, we often rely on 1-Dalbig via the CLT, or check if the original population data looks reasonably normal if n is small.
So random, independent, 10%, normal, large enough, check those conditions every time.
Every single time. If they aren't met, you need to proceed with extreme caution, or perhaps use a different statistical method altogether. These conditions ensure the validity of our p-values and confidence levels.
Okay. So in Units 6 and 7, we apply these powerful inference procedures, confidence intervals, and hypothesis tests to different types of data. Unit 6 focuses on proportions, right? Categorical data.
That's right. Unit 6 is all about inference for one or two population proportions. We might use a one-proportion z-test to ask questions like, is there significant evidence that more than 50% of the population approves of this new policy? Or we could use a two-proportion z-interval to estimate the difference between the support levels for a candidate among men versus women.
Using z procedures because we're dealing with proportions.
Correct. Then Unit 7 shifts to inference for means when our variable is quantitative.
Like average height, average weight, average score.
Exactly. Here, because we usually don't know the true population standard deviation, we have to estimate it using the sample standard deviation. This introduces a bit more uncertainty, so instead of using a normal z distribution, we use a related distribution called the t-distribution.
Ah, the t-distribution. Looks similar to normal, but with fatter tail.
Precisely. It accounts for the extra uncertainty from estimating sigma. So in Unit 7, we use one-sample t-tests and t-intervals. For instance, testing if the average weight of a manufactured product is significantly different from the claimed 10 ounces. Or we use two-sample t-tests and t-intervals to compare the average heights of two different plant species grown under different conditions.
Comparing two group means.
And a particularly clever application here is the paired t-test or paired t-interval. This is specifically designed for situations where you have two measurements on the same individual or matched pair.
Like a before and after study.
Perfect example. Did a specific training program actually increase the average performance score for each individual participant? You'd analyze the differences in scores for each person using a paired t procedure. It's very powerful for controlling individual variation.
Okay, so Z for proportions, T for means, usually. That covers Unit 6 and 7. What about Unit 8?
Unit 8 takes us back to categorical data, but now often involving more than two categories or groups. This is the realm of chi-square tests.
Chi-square. Sounds Greek.
It is. The core idea behind all chi-square tests is to compare the counts of observations we actually observed in different categories to the counts we would expect to see if a certain null hypothesis were true. We're asking, are our observed counts significantly different from what we'd expect purely by chance?
Observed versus expected counts. How does that work?
We calculate a chi-square statistic, which basically sums up the squared differences between observed and expected counts, relative to the expected counts, across all categories. A large chi-square value means our observed counts are far from what we expected under the null, providing evidence against $.
What kinds of questions can chi-square tests answer?
There are three main types. First is the chi-square goodness of fit test. This tests if the observed distribution of counts in a single categorical variable fits some hypothesized distribution.
Like your M&M's example earlier, checking if the bag's color distribution matches the company's claim.
Exactly. Does our sample of M&Ms fit the claimed proportions for each color. That's a goodness of fit test.
Okay, what are the other two?
The other two deal with relationships between two categorical variables. We have the chi-square test for homogeneity. This compares the distribution of a single categorical variable across two or more different populations or groups.
Homogeneity, like, are the distributions the same?
Precisely. For example, you're testing 3 different dosages of a pain relief drug. You could use a test for homogeneity to see if the distribution of patient responses, for example, no relief, some relief, complete relief, is the same across all 3 dosage groups.
Comparing distributions across groups. Got it. And the last one.
The chi-square test for independence. This tests whether there is an association or relationship between 2 categorical variables within a single population.
Independence, like, are the 2 variables unrelated?
Exactly. For example, you take one sample of adults and record 2 variables for each person: their preferred social media platform, Facebook, Instagram, TikTok, etc., and their primary news source, TV, online, print. You could use a test for independence to see if there's a statistically significant association between preferred social media and primary news source in that population. Are they related or independent?
Wow, chi-square seems really versatile for categorical data. Used in market research, maybe?
Hugely. Market research, A/B testing and web design, which button color gets more clicks, quality control, even genetics. Do observe gene frequencies match expected Mendelian ratios? Very widely applicable.
Okay, that's Unit 8. We're almost there. What's in the final unit, Unit 9?
Unit 9 brings us full circle, back to relationships between 2 quantitative variables, connecting back to Unit 2 where we first looked at scatter plots and correlation. Unit 9 is about inference for quantitative data. Slopes.
Inference for the slope of a regression line.
Exactly. Remember back in Unit 2, we learned how to calculate the correlation R and find the least squares regression line to describe a linear relationship in our sample.
Yep. Slope B told us the relationship in the sample.
Well, Unit 9 asked the bigger inference question. Is the linear relationship we observed in our sample strong enough evidence to conclude there's a real linear relationship in the entire population? Is the true slope of the population regression line, often denoted by the Greek letter beta, beta, truly different from 0?
Because if the true slope beta is 0, it means there's no linear relationship in the population, right? X doesn't help predict Y linearly.
Precisely. So we often perform a t-test for the slope. The null hypothesis is typically H dollars. Beta equals null. No linear relationship in the population. And the alternative is usually ha. Beta neck dollar. There is some linear relationship. Or perhaps one-sided if we have a specific direction in mind.
And we get a p-value just like other tests.
Yep. A small p-value suggests we reject d-Challenger beta and conclude there is significant evidence of a linear relationship between the 2 variables in the population.
Can we get a confidence interval for the slope, too?
Absolutely. We can construct a confidence interval for the slope. This gives us a plausible range of values for the true rate of change in the population. For example, we could be 95% confident that for every $1 increase in advertising spend, sales increase by somewhere between $2.50 and $4 on average.
That sounds incredibly useful for business decisions. Does advertising significantly increase sales? Does temperature significantly affect energy consumption?
Those are exactly the kinds of questions inference for slope helps answer. And just like with all other inference procedures, there are crucial conditions we must check to ensure our results are valid, often remembered by the acronym LINER.
LINER. Okay, what does that stand for?
Linear. The underlying relationship in the population should actually be linear. Check the scatter plot and residual plot. Independent. Residuals should be independent of each other. Normal. Residuals should be approximately normally distributed. Equal variance. The spread of residuals should be roughly the same for all x values. Check the residual plot for fanning. Random. Data should come from a random sample or randomized experiment.
LINER conditions for regression inference. Got it. Need to check those too.
Always check the conditions.
Wow. Okay, this deep dive, it might feel like a lot to take in, right?
Right.
We've really journeyed through the entire landscape of AP statistics today, from just describing single variables all the way to making these incredibly sophisticated inferences about vast populations. And we've tried to uncover the powerful real-world applications at every single turn.
It's a comprehensive field, no doubt.
But the true beauty of AP statistics, I think, isn't just in mastering these individual concepts or formulas. It's profoundly in the mindset it cultivates.
I agree completely.
It's really about equipping you, our listener, with the indispensable tools to critically evaluate information, whether it's a groundbreaking scientific study you read about, a headline-grabbing news report, a persuasive marketing claim you see, or even just a casual conversation you overhear.
Yeah, if we connect this to the bigger picture,
Mm-hmm.
this body of knowledge genuinely transforms you. You become a much savvier, more discerning consumer of information.
Savvy and discerning, I like that.
It fosters this powerful spirit of inquiry and, maybe more importantly, a healthy, informed skepticism. You learn to stop just taking numbers or claims at face value.
Right. You start asking questions.
Instinctively, you start asking, wait a minute, how was this data actually collected? What are the potential biases that might be lurking here? Can they really claim causation based on this study design? Or is this just an association they found? What are the possible errors they might have made in reaching that conclusion? It's a profound shift in how you engage with the world around you.
And it's not just about critical thinking, right? It's also about developing practical strategies for truly learning and applying this information effectively. Our sources really emphasize that statistics is very much a doing subject.
Oh, absolutely. You can't learn statistics by just reading about it. You have to consistently practice and problem solve.
Like learning a sport, you said earlier.
Exactly. You don't become a great basketball player by just reading the rule book. You have to get out there and practice your free throws, practice your dribbling, work on your game strategy. For statistics, that means working through lots and lots of practice problems, especially those open-ended free response type questions that really force you to think critically, interpret results, and apply the concepts in context.
And you absolutely must think like a statistician, not just like a student trying to memorize steps for a test.
That's a key distinction. Don't just crunch numbers without context. Always strive to tell the story that data reveals. Every conclusion you write should be phrased clearly with respect to the specific problem scenario. Always ask yourself, okay, what does this p-value or this slope or this confidence interval actually mean in the context of this problem? Explain it in terms of, blood pressure or salaries or M&M colors.
And critically, master the core concepts, not just the formulas. That seems huge.
It is. The why is almost always more important than the what or the specific formula. Understand why a larger sample size reduces the margin of error. Understand why we check the 10% condition. Understand why we use a t distribution instead of a z distribution when sigma is unknown. It's that deeper conceptual understanding that truly empowers you to apply statistics correctly in new situations.
Your graphing calculator becomes pretty essential too, doesn't it? Truly your best friend in this statistical journey.
Indispensable. You need to use your calculator wisely. Get incredibly comfortable with its built-in statistical functions, calculating means, standard deviations, correlations, running hypothesis tests, making confidence intervals. It can do so much of the heavy lifting for the actual calculation.
There's a but, isn't there?
There is. But, and this is key, you also need to understand what the calculator is doing behind the scenes. Don't just mindlessly punch in numbers following a recipe without comprehending the underlying statistical process. Know which text you're running and why, and know how to interpret the output it gives you. It's a tool, not a magic box.
Good point. And this next strategy is one we can all relate to, I think, because it's just fundamental to how humans learn. You have to analyze mistakes and learn from them.
Oh, absolutely crucial. Every single mistake is a precious learning opportunity. Seriously. When you get something wrong on a practice problem or a quiz, don't just sigh and move on.
Dig into it.
Dig into why you got it wrong. Was it a conceptual misunderstanding of what a p-value represents? Was it a simple calculation error? Did you misread the question or miss a key detail? Did you forget to check the conditions? This kind of reflective feedback loop is absolutely essential for genuine improvement and achieving deeper mastery.
And finally, actively seek out those real-world connections. Statistics is truly everywhere once you start looking for it.
It really is. When you see a poll result in the news, think about the margin of error and what it implies about the confidence interval. When you read about a medical trial for a new treatment, think about the experimental design. Did they use blinding? Random assignment? What about potential biases?
This active engagement makes data your ally, like you said, and it makes the whole learning process so much more interesting and meaningful, doesn't it?
It really does. It stops being just abstract math and becomes a lens for understanding the world.
And here's a super modern really practical tip for learning AP statistics, or honestly, any complex subject you're trying to get your head around these days, using AI like ChatGPT as your on-demand tutor.
It's an incredible resource, it really is, if you use it effectively and smartly.
How can you use it effectively? Give us some examples.
Well, for instance, if the central limit theorem just isn't clicking for you, maybe the textbook explanation is too dense. You can ask ChatGPT something like, explain the central limit theorem and why it's important in statistics, breaking it down into simple, easy-to-understand parts, maybe with an analogy. It can often rephrase complex ideas into more digestible language.
Getting different explanations, that's helpful.
Yeah. You can also use it to check your own understanding. Try explaining a concept to ChatGPT in your own words. Say, okay, I think a type I error is when you fail to reject a true null hypothesis. Is that correct?
Yeah.
It will immediately correct you if you're wrong, clarify the definition, and provide that instant personalized feedback that's often hard to get otherwise.
That's cool, like having a study buddy who knows the answers. What else?
What's truly amazing is that you can even get custom practice problems with solutions. You can prompt it. Generate a practice problem for me that involves interpreting a confidence interval for a slope in a real-world context, and then provide a step-by-step solution showing the interpretation. It can create a realistic scenario and walk you through the entire solution process, showing you exactly how to set up the problem, identify the key numbers, and interpret the result in context. This is incredibly helpful when you've run out of textbook exercises or just need more focused practice on a specific topic.
Wow. Unlimited practice problems on demand. That's powerful.
And if you're stuck on a particular problem, instead of just asking for the final answer, which doesn't help you learn, you can get step-by-step guidance. Try prompting it, something like, here's the problem I'm working on. I've calculated the test statistic, but I'm unsure how to find the p-value using my calculator model. Can you give me a hint or nudge me in the right direction? It can often provide just enough assistance to get you unstuck without simply giving away the whole answer.
Getting hints, not just answers. Smart.
You can also simulate quizzes. Ask it to quiz you interactively on, say, Unit 3 concepts, or the difference between Type I and Type 2 errors. It can ask you questions, evaluate your answers, and help you identify areas where you're still weak. And maybe one of the most powerful techniques for deep mastery, one that really forces true understanding, is the teaching role. Try to explain concepts back to the AI. If you can teach it clearly and concisely explain hypothesis testing from start to finish, for example, you know you truly understand it yourself. It's a fantastic way to solidify your knowledge and spot any lingering gaps or fuzzy thinking.
Okay, using AI as a tutor sounds incredibly useful. But there has to be a crucial caution here, right? This cannot be overstated.
Absolutely. Always, always, always. Verify information you get from AI with reliable, trusted sources, your textbook, your teacher, reputable websites. AI models can sometimes make mistakes or hallucinate or present information in a way that's subtly incorrect. Use it as a powerful learning aid, sophisticated study partner, but never as a crutch or, obviously, for cheating. The ultimate goal, the true superpower we talked about, is your mastery, your understanding, and your ability to think statistically for yourself.
Your brain has to do the learning.
Exactly. Ultimately, as we often say on these deep dives, knowledge is most valuable when it is truly understood and then purposefully applied. This deep dive into AP statistics, hopefully, has armed you with a profound new way of seeing the world.
A new lens.
A new lens, exactly. One that instinctively questions assumptions, that actively seeks the deeper truths hidden behind the numbers, and that leaves you incredibly well equipped to navigate the data-saturated landscape of modern life with real confidence.
We've definitely journeyed through the entire landscape today, haven't we? From the initial steps of describing single variables, through the crucial methods of collecting good data, understanding that dance of chance with probability, and finally, making those sophisticated inferences about entire populations. We've tried to uncover the surprising, practical, real-world applications at every single turn. You really do now possess a comprehensive mental toolkit for navigating our data-saturated world.
And this knowledge isn't just academic theory locked away in a textbook. It is incredibly empowering for your daily life. It enables better decision-making, it fosters a much more critical evaluation of the claims you encounter constantly, and hopefully it cultivates a lifelong habit of curious, informed learning.
So what does this all mean for you, our listener? We want to invite you to consider this, maybe as a final provocative thought. Next time you see a political poll result flash across your screen, or you encounter a new health claim in an article, or maybe you hear about a social study being discussed on the news, What new questions will you ask now? How will you use these incredibly powerful statistical tools and concepts we've unpacked today to try and uncover the deeper story, the real truth that might be hiding behind those numbers?
Will you ask about the sample size, the margin of error, how the data was collected, potential biases, whether they can really claim causation?
Exactly. We truly hope you use this new statistical compass to explore the world with greater insight, renewed confidence, and maybe even a lifelong sense of discovery. Thanks so much for joining us on this deep dive.